Hi, this is the video tutorial for TITAN-6-3M cam. Okay, the first thing you're going to do is you're going to need to have Fusion running, of course, and we're going to open our data panel, and you're going to navigate to your instructors folder. You should be either be able to download the model, or you should be able to copy it over to your own folder project, and select copy, and you can go back up, and in my case I'm using a demo folder, and it should appear in your list of projects. You can double click on the model to open it, and then minimize the data panel to give you more room. Okay, so this is a circular part with 5 square bosses and some bolt clearance holes. Okay, I believe these are 1032s, and these are 1/4 inch through holes. Okay, so the first thing we're going to do is we're going to switch from model mode to a manufacturer mode. And we're going to create a setup. And we're going to set our stock parameters. Our side offset is 0.025, which should give us a 2 inch by 2 inch square. And our stock top offset, we're going to leave it at 0.04. And our bottom offset is going to be a difference between 0.79 and 1 inch, because that's the height of our stock, which is going to give us 0.21 as a bottom offset. So we should have a block that's 2 inch by 2 inch by 1 inch. Moving up to our setup, we're going to set our origin. And like we have in the past, we're going to set this off stock for our first operation. And it's going to be a stock box point in this corner here. Now, because it's a circular part, we should have our X and Y coordinates as shown. If they're not, you'll need to manipulate the position of X and Y so that it's as shown in the image here. We're going to go to post process, and we're up to 51 is our program number, and we're going to call this operation 1 with a work offset of 1. So we've created our first setup. We're going to say OK. And as usual, this should be a review for you. You're going to go do a facing operation. And you're going to select tool 1 from the Titan library, which is a 3 inch face mill. And we're going to go 4,000 RPM, and we're going to go ahead and bump this up to 40 inches a minute. A little faster than you've been going. And 20 on our plunge rate and ramp rate. Geometry, there's nothing to select, so you can skip that tab and go to heights. All of this should be at default. We move on to passes. 4/10 tolerance is fine. Pass direction, we're going to go 90 degrees. Pass extension 1.6, little over half the diameter of the cutter. Stock offset we're going to leave alone. Step over we're going to leave alone. The rest of these we are going to select from other side. We hope that the cutter pushes against the fixed jaw after you render it. If it's going the opposite way, going against the adjustable jaw, you'll have to come back and toggle the switch the opposite way. We're just taking 40 thousandths off, so we're not going to do multiple depths, and we're not going to leave stock. We're going to go to linking now. All of these first are at default. And then we're going to have a lead-in entry. We're not going to need a vertical lead-in entry, and our lead-in and out are going to be the same. Transition type should be smooth, and we select OK. So we go down and we're going towards the fixed jaw devices, which is what you want. If these arrows are reversed, then you'll want to go back and change that checkbox. Okay. All right, moving on. We're going to do another 2D adaptive clearing. It's going to remove the majority of the material around here. Before we do that, let's inspect a few things. We want to know how much distance is between here and here so we know what size cutter can fit through there. So it's 0.275, so a 1/4 inch cutter can barely fit through there. So what I'm going to suggest is we go through with a adaptive clearing with a 3/8, and then we do our finishing with a 1/4 inch cutter, which should be able to finish off the rest of that top. Okay, so we're going to close that. So we're going to go to 2D adaptive clearing. And we're going to go and we're going to select from the Titan library our 3/8 end mill, flat end mill. We're going to do a spindle speed of 4,000. Actually, I'm going to show you at this point how to set the speeds of feeds in here in Fusion. So when you go to select the tool, you can go over here, and on the right it has a link to the website for Kennametal with the product link. So if you select on that, you will get their website. You can just close this, it doesn't really matter, but this is their entire product line. And this is where you're going to get your feeds and speeds information. So we're looking at a 3/8 diameter tool, and it's in this column here, and the rows are by number of flutes. So we're using 3 flute cutters, and we have a chip load of 0.0024. So we're going to take that number and we're going to see if we can copy and paste that. So we're going to go copy. That's Control-C on your keyboard, and then we'll minimize that, and we'll close this, and you're going to put that chip per tooth right here where it says feed per tooth. And then we're going to go back to our website, and we're going to look at our surface footage. So the cutting surface feet per footage per minute is a minimum of 1,640 to 4,920. So in general, it really depends on the horsepower of your machine and such. So we'll take this high number and compare that to what we have over here in Fusion. So right now we have 392 feet per minute. If we were to replace that value with that figure, we would have to be running at 50,000 RPM at that chip load, and we could get a cutting feed rate of 360 inches a minute. So I don't think we're going to be able to achieve that, not with our equipment. So we're going to not use that, but we're going to put in an RPM that we think we can do. Alright, so we at 8,000 RPM at that chip per tooth, we should be getting a cutting feed rate of 57 inches a minute. Okay, so let's go ahead and use that. This is going to be a roughing cutter. We'll go 57, 57, and then we'll go half of that. So we'll go 20, let's just go 23 and 23. This cutter will probably have the longest cycle time, so or at least the most area it's going to need to cover. But that's how you can use the calculation. You can put in various different boxes, and it'll auto-calculate the other ones. Now our surface feed per minute here is out of the range of what they recommend. Okay, so we get derives at 8,000 RPM at a chip per tooth for three flute cutter at 57.6 inches a minute. So we're gonna duplicate that number for our lead in and our lead out, and we're gonna take that number and divide it by half, which would be, I don't know, let's put 23 inches a minute, a little bit slower. 23 inches a minute for ramp, feed rate, and plunge. Okay, we're going to move on to geometry. Our pocket selections are going to be the bottom of the part, and then that surface of the part, leaving the squares as islands. Okay, we're going to move on to, we're going to leave all the rest of these at default. We're going to move on to heights. And we're going to change these to model top because the top's been machined down to model top. And selected contours will be the bottom heights. Okay, we're going to move on, and we're going to go to our passes. 4 thousandths tolerance, an optimum load of 0.15. We're going to leave that at default. Minimum cutting radius. That's fine, 0.0375. We're going to try using slot clearing. I'm not sure how that's going to work. And actually that won't work. We're going to climb cut. We're going to go multiple depths. Our maximum step depth is going to be 0.25. And we're going to go by order by depth. And stock to leave, we're going to leave 0.01 on our sides and top and bottom there. We'll go ahead and select smoothing, and then we're going to move on to the next tab. We're going to leave these at default. Our non-engagement feed rate we do want at 57 inches a minute. Our horizontal lead in, we're gonna bump that up to 0.1, and we can leave a vertical lead in for this. I don't think it'll make a big difference, but ramp type helix, 2 degrees, ramp taper angle 0, ramp clearance height 0.1 is fine. Our helical ramp diameter 0.356. We'll just leave those all at default. And then entry positions, we're going to put an entry position in here at the front. We want to make sure that it's, if our material saw cut wide, we're not plunging there. And this also allow the operator to see the work. And then we'll hit OK. Okay, so we have our 3D adaptive clearing, and it cleared out most of the top. It didn't get into these slot areas, but it did a pretty good job of roughing all that out, leaving 0.1 all the way around. All right, so now that we're using the 3/8 end mill, we're going to go ahead and finish off the outside diameter with that cutter before moving on to the next thing. So we're going to do a 2D contour, and we're still using that 3/8 end mill. And we'll go ahead and leave the feed rates as what we have for that cutter. And then we're going to move on to geometry. We're going to select the bottom of our profile. We're going to move on to heights. We're going to set these to model top, since the top of the model's already been machined down to finished size. And we're going to go negative 0.01, 10 thousandths lower than our bottom offset, so that we can try to eliminate flash on the second side of this part. We're going to go to passes, 4/10 tolerance. We're going to climb cut. We're going to use wear compensation. We're going to skip all this stuff, and we're going to go down to roughing passes, we're not going to do any roughing passes. We've already done that. We are going to do multiple depths. We're going to go on 0.25 increments, and we're going to do one finish step down, and it's going to be at 0.01. It'll effectively become a spring pass. No wall taper angle. Approach mode along wall. Finish only at final depth. We're going to rough at final. We're going to use even step downs. Order by islands is irrelevant because we didn't select any. Stock the lead, we're not going to have any. We're going to select our smoothing. And then we move on to the next tab, which is our linking tab. We're going to leave all the first boxes at default. We're going to have a lead-in entry. Let's go ahead and bump that up to 0.1 on the radius and 0.1 in the linear. We're not going to do a vertical lead-in radius. And we want to exit out at the same length as lead-in. We're not going to do a ramp. We are going to do an entry position of the front of the part. And then we'll select OK. So this should be pretty straightforward. It's doing a finish pass just around the outside diameter before we move on to a smaller tool. Okay, so moving on to the next, we're going to do a 2D pocket to finish cleaning up all these bosses. There's a couple ways you could approach it, but we're going to use a pocket. So we're going to use our 1/4 inch flat end mill from the Titan library. 4,000 RPM, we're going to go 25 inches a minute, and half that on our plunge and our ramp rates. We'll go to geometry, we're going to select this plane here. And it automatically selects the boundaries as islands for the bosses. Okay, so we have our clearance height, this is default. Model top, we're going to bump our offset up to 0.3, and same thing with our feed height, 0.3, because we're planning on using a helical plunge. It needs a little more room. Model top for our top height, selected contours is our depth. We're going to go on to passes. We're going to left, we're going to climb cut, 0 minimum radius, and our maximum step over is going to be 80% of the cutter diameter. So getting out our handy dandy calculator, we're going to be using a 0.25 diameter end mill, and we're going to times that by 0.8, which is our factor for 80%, which leaves us 0.2. So we're going to put 0.2 in our maximum step over, and we're going to leave the rest of these at default. Our smoothing deviation, we are going to bump that up to 4/10 because we're not really doing a side finish. Okay, we're going to select multiple depths. We're going to go 0.25. We're going to do one finishing step down, and our step down is going to be 0.01. No taper angle. We're going to use even step downs. We're going to order by depth. Stock to leave, we're going to set that at 0 and then deselect the box. And we're going to select smoothing, 4/10 tolerance. We're going to move on to the linking tab. All the first ones at default are horizontal lead-in radius. We'll leave those at default, it's linear lead-in. Our vertical lead-in radius, we don't want one. We're going to go to 0. And our lead in and out is going to be the same. Our ramp type's helix, 2 degrees. Maximum roughing step 1. Ramp step 1. Ramp clearance height, helix, 0.1. Ramp radial clearance, 0. Helical diameter, 0.2375. We're going to leave entry positions alone. We're going to set OK. Okay, so we have our paths cleaning up the floor and each subsequent boss feature. Okay, so now that we've done that, we are down to chamfers and holes. Alright, so we have two different hole sizes on this part. And it looks like we have a large hole, which is our 1/4-inch clearance hole. So we're going to need to use the 3/8 chamfer mill to do the spot drilling for that one. So on this part, we're going to use the 3/8 chamfer mill for everything we can. And or we'll start with our deburring. Okay, so we're going to go 2D 2D chamfer, and we're going to select the 3/8 chamfer mill. Okay, so we're going to leave our RPMs alone. 20 inches a minute's good, and same thing with our lead-ins. Same scheme, 20, 20, and half of that for the ramp and plunge. For geometry, we're going to select the bottom contour of each of the boss features. Okay, and we're looking at plan view, make sure our arrows are on the correct side. Okay, so we're going to go to heights. Our retract height is going to be based off model top. Our feed height is also going to be based off model top. Our top height is going to be model top. Our bottom height is also going to be model top. Okay, moving on. We're going to try using compensation on here of wear. We're going to have a chamfer width of 10 thousandths, a chamfer tip offset of 0.04, and a chamfer clearance of 0. We're going to select smoothing, and we're going to move to the linking tab. We're going to leave these all at default. Horizontal lead-in radius of 0.0375, linear lead-in radius of 0.0375, and we want to deselect perpendicular, and we'll select OK. And it looks like all of our lead-ins are away from the actual part. Okay, moving on to the next chamfer routine. We're going to actually duplicate this toolpath. So we're going to use this similar parameters. We go into Edit. Same tool, so all the parameters there should be there. Geometry, we're going to clear that out, and we're going to select the bottom profile of the chamfer mill for the chamfer. We're going to our heights. We're going to keep all these at the retract and feed height at model top, but our top height on this one is going to be a selection, which is this plane. And then our bottom height is also going to be a selection of the same plane. Okay, moving on to the next tab. We're going to have to just select in computer for the wear compensation, which means we won't be using a lead in and lead out transition. Okay, so similar to the last one we did where we have features our chamfer mill can hit, we need to extend our chamfer tip offset. So the cutter we're using now is a 0.375 diameter. Divided by 2 means that if we were cutting right to the tip, it would have 0.1875 hanging over. Now we're going to subtract the 10 thousandths that we're removing for the chamfer itself, and that leaves 177 thousandths 5/10. So we're going to set our chamfer offset close to that number. So what we'll do is we'll set it at 0.17 and see if Fusion will generate the path in a circle. Okay, we go to linking tab, and we're going to leave all this at default, and we're going to deselect our lead-ins and lead outs. We're going to select OK. Okay, and so we have a pass all the way around. It's always good to look at it in a side view and go to the simulate. Make sure your stock is off and run our simulation. And you can pause it when it gets to the side. I actually want to look at one of these bosses from an angle that shows it. So as you can see, we only have a small amount of that chamfer mill engaging the work itself. I still can't explain the couple places that it's in midair and it thinks it's gouging against something, so I'm going to chalk that up as a glitch. Alright, so now we've finished all that. So now we have two different chamfer diameters we're going to lead in on these threaded holes and the bolt clearance holes. So we'll do the highest level first, and let's inspect the diameter. So the small holes, the diameter is 0.18, and the larger diameter is 0.27. Okay, so we'll need those two numbers a little bit later. So we're going to go drilling. We're going to drill, and we're going to keep with our 3/8 chamfer mill. 4,000 RPM and 10 inches a minute is reasonable for this. We're going to use geometry. We're going to select the small chamfer first, and then we're going to select same diameter, so it'll get all the holes of that same diameter. If we had holes at the same size, we could then select these, but since they're a different size, we need to do those in a different routine. Okay, so on heights, our retract is model top. Our feed height is going to be based off top height. Our top height in this case will be the top of the hole. Our bottom of the hole is going to be based off top of the hole, and we're going to put in a negative offset of half the diameter, which was negative 0.09. Okay, go to the next tab, and we're going to change to a counter boring cycle, and we're going to use a 1 second dwell. I'll select OK. And now we'll go ahead and actually we're going to duplicate this toolpath, and we're going to open that toolpath and edit it. We're going to clear our selections. Well, we're going to select the larger holes. Okay. Now we're going to go on to heights. Okay, so our retract's model top. Our feed height is going to be model top. Our top height is going to be actually a selection, because we want to select that face. And the bottom of the hole is going to be selection. And this time the offset's going to be bigger. It's going to be half of 0.27. So half of 0.27 would be negative 0.135. Okay, we're going to go on to the next tab, and we'll leave that all at the same defaults we had before. So we'll have a 1 second dwell. We're going to select OK. And we should have rapids that, you know, go above the boss features. Okay. All right. So now we'll move on to drilling. So we need to drill out these holes, and then we need to tap them, and then we need to drill out these holes. So we're going to go drill, and we're going to select the tap drill for a 1032, which is going to be our tool number 10, 177 thousandths. Okay, 4,000 RPM is fine. We're going to go 10 inches a minute on this drill because it's smaller. Geometry, we're going to select one of the holes. We're going to select same diameter so it picks up all of them. Move on to the next tab. Retract is going to be model top. Feed height is going to be model top. Top height, model top. Bottom height, hole bottom, and we're going to select drill tip through bottom of hole, so it'll extend it by the tip of the drill bit. We'll move on to drilling. We're going to do a deep drilling with full retract, and a peck depth of 0.04 is good for that cutter, and the rest of the boxes can stay at default. We'll select OK. Now we're going to go and do drilling again, and we're going to select our 1032 tap. So we go to tool number 13, our 1032 right hand tap. We're going to leave this at 500 RPM. We're going to be switching to roll taps, so I think we should go a little slower on them. And we'll leave the surface speed alone. Geometry, we're going to select a cylinder and same diameter. And we're going to go to heights. Again, we're going to go model top, model top, model top, and this one's going to be model top as well. And then we're going to punch in our offset, which is, they wanted 150 thousandths deep, and we're going to put a 3 leads on that, so we need to do another 100 thousandths. So we're going to go 0.25 negative. Okay, that should give us our thread depth. We're going to go to cycle, and we're going to do right hand tapping, no dwell. And we're going to select OK. Now our final operation for this side of the part is going to be another drilling. So 2D drilling, we're going to select our 1/4 inch drill, which is tool number 8. And we'll go 4,000 RPM, 18 inches a minute, fine for that one. And then we're going to go to our hole faces. We're going to select one of the big holes. And we're going to select same diameter. On our heights, we're going to go to model top, model top. So our top height is going to be based off selection. And we're going to select the plane where our holes start. And then our bottom height is going to be based off the bottom of the hole, which is fine. And we're going to select the box that says drill tip through. And we want to make sure that it breaks all the way through. So right now we just have the tip coming through. So I'm going to put in a breakthrough depth of 0.1. and that makes sure that your drill bit goes all the way through the part. You do want to be careful with your parallels. You want to make sure they're up against the vise jaws or you'll drill into your parallels with this operation. Next tab, we're going to do another deep drilling. And with this one, yeah, we can go a 1/16 per peck and that's fine. And we'll select OK. Alright, so we're done with that. Let's simulate what we've done so far. And we'll display our stock. And we'll hit go. So our 2D adaptive is coming in and roughing a bunch of material. Looks like we might be leaving, no, we're not leaving some material in the corners, thought we were. It's going to come down and relieve most of the material around the part. Okay, now it's coming and it's doing its finishing cut around the exterior of the part. And now the 1/4 inch end mill is coming in and doing its 3D pocket. And part of that pocket, it's going to finish each of the bosses. Now our chamfer mill's coming over and doing the chamfers on the tops of the bosses. And then it's coming over and should be doing the sides with the top edge of the chamfer mill. Okay, now it's going to come over and it should spot the threaded holes. And then it's going to spot the 1/4 inch clearance holes. Okay, we're going to skip the peck drilling, come in and tap our holes. I'm going to skip this, and it drilled through our part. Okay, so the next thing I'm going to show you is how to renumber these tools so you can load them more efficiently in your tool changer. So you can, there's a process of reordering the tools, and it's done through managing your tool library. So you go to Tool Library. And you're going to make sure that you have your document highlighted, so it'd be the name of your file. And you come over and highlight your tool lists that are used in that document. Right click, and you're going to say Renumber Tools. Or you can press Control R apparently. And renumber the tools. We're going to start with tool 1, and the increment is going to be 1. We're going to update the diameter offset, length offset, and compensation offset. So in our G code, we want them all to be synchronized. And we're going to hit OK. So now I've just very quickly numbered my tools 1 through 7. We're going to hit close, and we look at our list, and we now have tools 1 through 7. So they'll still be registered to the tool type for the Titan library, the main library, but for the purposes of this program, you would put them in positions 1 through 7. Okay, so the next step is you're going to machine the backside. what I'd like you to do is refer to the previous video for TITAN-6-3M second setup and duplicate the same operations you used in that program for this one. So you'll make a setup 2 on your own, and you'll go in, I believe, with a 1/2 inch end mill and generate a pocket that'll mill off the back face. The height of this part's the same, so the geometry should be the same. We'll hold it in the same soft jaw. But again, you can reference the previous video and programming notes for all the settings. I'll see you on the next one.